Lead. Lead is a chemical element with symbol Pb and atomic number 82. It is a heavy metal that is denser than most common materials. Lead is soft and malleable, and also has a relatively low melting point. When freshly cut, lead is silvery with a hint of blue. It tarnishes to a dull gray color when exposed to air. Lead has the highest atomic number of any stable element, and 3 of its isotopes each conclude a major decay chain of heavier elements. Lead is a relatively unreactive post-transition metal. Its weak metallic character is illustrated by its amphoteric nature. Lead and lead oxides react with acids and bases, and it tends to form covalent bonds. Compounds of lead are usually found in the +2 oxidation state rather than the +4 state common with lighter members of the carbon group. Exceptions are mostly limited to organolead compounds. Like the lighter members of the group, lead tends to bond with itself. It can form chains and polyhedral structures. Lead is easily extracted from its ores. Prehistoric people in Western Asia knew of it. Galena, a principal ore of lead, often bears silver, interest in which helped initiate widespread extraction and use of lead in ancient Rome. Lead production declined after the fall of Rome and did not reach comparable levels until the Industrial Revolution. In 2014, the annual global production of lead was about 10 million tons, over half of which was from recycling. Lead's high density, low melting point, ductility, and relative inertness to oxidation make it useful. These properties, combined with its relative abundance and low cost, resulted in its extensive use in construction, plumbing, batteries, bullets and shot, weights, solders, pewters, fusible alloys, white paints, leaded gasoline, and radiation shielding. Lead is toxic, and its use was phased out of some applications after this was discovered. However, many countries still allow the sale of products that expose humans to lead, including some types of paints, bullets, fireworks, and brass taps. Lead is a toxin that accumulates in soft tissues and bones. It acts as a neurotoxin, damaging the nervous system and interfering with the function of biological enzymes, causing neurological disorders, such as brain damage and behavioral problems. A lead atom has 82 electrons, arranged in an electron configuration of 4f145d106s26p2. The sum of lead's first and second ionization energies, the total energy required to remove the two 6p electrons, is close to that of tin, lead's upper neighbor in the carbon group. This is unusual. Ionization energies generally fall going down a group, as an element's outer electrons become more distant from the nucleus, and more shielded by smaller orbitals. The similarity of ionization energies is caused by the lanthanide contraction, the decrease in element radii from lanthanum to lutetium, and the relatively small radii of the elements from hafnium onwards. This is due to poor shielding of the nucleus by the lanthanide 4f electrons. The sum of the first 4 ionization energies of lead exceeds that of tin, contrary to what periodic trends would predict. Relativistic effects, which become significant in heavier atoms, contribute to this behavior. One such effect is the inert pair effect. The SiXs electrons of lead become reluctant to participate in bonding, making the distance between nearest atoms in crystalline lead unusually long. Lead's lighter carbon group congeners form stable or metastable allotropes with the tetrahedrally coordinated and covalently bonded diamond cubic structure. The energy levels of their outer s and p orbitals are close enough to allow mixing into 4 hybrid sp3 orbitals. In lead, the inert pair effect increases the separation between its s and p orbitals, and the gap cannot be overcome by the energy that would be released by extra bonds following hybridization. Rather than having a diamond cubic structure, lead forms metallic bonds in which only the p electrons are delocalized and shared between the Pb2+ ions. Lead consequently has a face-centered cubic structure like the similarly sized divalent metals calcium and strontium. Pure lead has a bright, silvery appearance with a hint of blue. It tarnishes on contact with moist air and takes on a dull appearance, the hue of which depends on the prevailing conditions. Characteristic properties of lead include high density, malleability, ductility, and high resistance to corrosion due to passivation. Lead's close-packed face-centered cubic structure and high atomic weight result in a density of 11.34 G/cm3, which is greater than that of common metals such as iron, copper, and zinc. This density is the origin of the idiom to go over like a lead balloon. Some rarer metals are denser. Tungsten and gold are both at 19.3 G/cm3, and osmium, the densest metal known, has a density of 22.59 G/cm3, almost twice that of lead. Lead is a very soft metal with a Mohs hardness of 1.5, it can be scratched with a fingernail. It is quite malleable and somewhat ductile. The bulk modulus of lead, a measure of its ease of compressibility, is 45.8 GPa. In comparison, that of aluminium is 75.2 GPa, copper 137.8 GPa, and mild steel 160-169 GPa. Lead's tensile strength, at 1217 MPa, is low. It can be strengthened by adding small amounts of copper or antimony. The melting point of lead at 327.5 degrees C is very low compared to most metals. Its boiling point of 1749 degrees C is the lowest among the carbon group elements. The electrical resistivity of lead at 20 degrees C is 192 nanometers, almost an order of magnitude higher than those of other industrial metals. Lead is a superconductor at temperatures lower than 7.19 K. This is the highest critical temperature of all type I superconductors and the third highest of the elemental superconductors. Natural lead consists of 4 stable isotopes with mass numbers of 204, 206, 207, and 208, and traces of 5 short-lived radioisotopes. The high number of isotopes is consistent with lead's atomic number being even. Lead has a magic number of protons, for which the nuclear shell model accurately predicts an especially stable nucleus. Lead-208 has 126 neutrons, another magic number, which may explain why lead-208 is extraordinarily stable. With its high atomic number, lead is the heaviest element whose natural isotopes are regarded as stable. Lead-208 is the heaviest stable nucleus. The 4 stable isotopes of lead could theoretically undergo alpha decay to isotopes of mercury with a release of energy, but this has not been observed for any of them. Their predicted half-lives range from 1035 to 10,189 years. 3 of the stable isotopes are found in 3 of the 4 major decay chains. Lead-206, Lead-207, and Lead-208 are the final decay products of uranium-238, uranium-235, and thorium-232, respectively. These decay chains are called the uranium chain, the actinium chain, and the thorium chain. Their isotopic concentrations in a natural rock sample depends greatly on the presence of these 3 parent uranium and thorium isotopes. For example, the relative abundance of lead-208 can range from 52% in normal samples to 90% in thorium ores. For this reason, the standard atomic weight of lead is given to only 1 decimal place. As time passes, the ratio of lead-206 and lead-207 to lead-204 increases, since the former 2 are supplemented by radioactive decay of heavier elements while the latter is not. This allows for lead-lead dating. As uranium decays into lead, their relative amounts change. This is the basis for uranium lead dating. Lead-207 exhibits nuclear magnetic resonance, a property that has been used to study its compounds in solution and solid state, including in human body. Apart from the stable isotopes, which make up almost all lead that exists naturally, there are trace quantities of a few radioactive isotopes. One of them is lead-210, although it has a half-life of only 22.3 years. Small quantities occur in nature because lead-210 is produced by a long decay series that starts with uranium-238. Lead-211, -212, and -214 are present in the decay chains of uranium-235, thorium-232, and uranium-238, respectively, so traces of all 3 of these lead isotopes are found naturally. Minute traces of lead-209 arise from the very rare cluster decay of radium-223, one of the daughter products of natural uranium-235, and the decay chain of neptunium-237, traces of which are produced by neutron capture in uranium ores. Lead-210 is particularly useful for helping to identify the ages of samples by measuring its ratio to lead-206. In total, 43 lead isotopes have been synthesized, with mass numbers 178-220. Lead-205 is the most stable radioisotope, with a half-life of around 1.5 times 107 years. The second most stable is lead-202, which has a half-life of about 53,000 years, longer than any of the natural trace radioisotopes. Bulk lead exposed to moist air forms a protective layer of varying composition. Lead carbonate is a common constituent. The sulfate or chloride may also be present in urban or maritime settings. This layer makes bulk lead effectively chemically inert in the air. Finely powdered lead, as with many metals, is pyrophoric and burns with a bluish-white flame. Fluorine reacts with lead at room temperature, forming lead fluoride. The reaction with chlorine is similar but requires heating, as the resulting chloride layer diminishes the reactivity of the elements. Molten lead reacts with the chalcogons to give lead chalcogenides. Lead metal resists sulfuric and phosphoric acid but not hydrochloric or nitric acid. The outcome depends on insolubility and subsequent passivation of the product's salt. Organic acids, such as acetic acid, dissolve lead in the presence of oxygen. Concentrated alkalis will dissolve lead and form plumbites. Lead shows two main oxidation states, +4 and +2. The tetravalent state is common for the carbon group. The divalent state is rare for carbon and silicon, minor for germanium, important for tin, and is the more important of the two oxidation states for lead. This is attributable to relativistic effects, specifically the inert pair effect, which manifests itself when there is a large difference in electronegativity between lead and oxide, halide, or nitride anions, leading to a significant partial positive charge on lead. The result is a stronger contraction of the lead SiXs orbital than is the case for the 6p orbital, making it rather inert in ionic compounds. The inert pair effect is less applicable to compounds in which lead forms covalent bonds with elements of similar electronegativity, such as carbon in organolead compounds. In these, the SiXs and 6p orbitals remain similarly sized and sp3 hybridization is still energetically favorable. Lead, like carbon, is predominantly tetravalent in such compounds. There is a relatively large difference in the electronegativity of lead at 1.87 and lead at 2.33. This difference marks the reversal in the trend of increasing stability of the +4 oxidation state going down the carbon group. Tin, by comparison, has values of 1.80 in the +2 oxidation state and 1.96 in the +4 state. Lead compounds are characteristic of the inorganic chemistry of lead. Even strong oxidizing agents like fluorine and chlorine react with lead to give only PbF2 and PbCl2. Lead ions are usually colorless in solution, and partially hydrolyzed to form Pb and finally 4+, but are not reducing agents as tin ions are. Techniques for identifying the presence of the Pb2+ ion in water generally rely on the precipitation of lead chloride using dilute hydrochloric acid. As the chloride salt is sparingly soluble in water, in very dilute solutions the precipitation of lead sulfide is achieved by bubbling hydrogen sulfide through the solution. Lead monoxide exists in two polymorphs, litharge alpha PbO and massicot beta PbO, the latter being stable only above around 488 degrees C. Litharge is the most commonly used inorganic compound of lead. There is no lead hydroxide. Increasing the pH of solutions of lead salts leads to hydrolysis and condensation. Lead commonly reacts with heavier chalcogons. Lead sulfide is a semiconductor, a photoconductor, and an extremely sensitive infrared radiation detector. The other two chalcogenides, lead selenide and lead telluride, are likewise photoconducting. They are unusual in that their color becomes lighter going down the group. Lead dihalides are well characterized. This includes the diastatide and mixed halides, such as PbFCl. The relative insolubility of the latter forms a useful basis for the gravimetric determination of fluorine. The difluoride was the first solid ionically conducting compound to be discovered. The other dihalides decompose on exposure to ultraviolet or visible light, especially the diiodide. Many lead pseudohalides are known, such as the cyanide, cyanate, and thiocyanate. Lead forms an extensive variety of halide coordination complexes, such as 2, 4, and the N5N chain anion. Lead sulfate is insoluble in water, like the sulfates of other heavy divalent cations. Lead nitrate and lead acetate are very soluble, and this is exploited in the synthesis of other lead compounds. Few inorganic lead compounds are known. They are only formed in highly oxidizing solutions and do not normally exist under standard conditions. Lead oxide gives a mixed oxide on further oxidation, Pb3O4. It is described as lead oxide, or structurally 2-PbO-PbO2, and is the best known mixed valence lead compound. Lead dioxide is a strong oxidizing agent, capable of oxidizing hydrochloric acid to chlorine gas. This is because the expected PbCl4 that would be produced is unstable and spontaneously decomposes to PbCl2 and Cl2 analogously to lead monoxide. Lead dioxide is capable of forming plumbate anions. Lead disulfide and lead diselenate are only stable at high pressures. Lead tetrafluoride, a yellow crystalline powder, is stable, but less so than the difluoride. Lead tetrachloride decomposes at room temperature. Lead tetrabromide is less stable still, and the existence of lead tetraiodide is questionable. Some lead compounds exist in formal oxidation states other than +4 or +2. Lead may be obtained, as an intermediate between lead and lead, in larger organolead complexes. This oxidation state is not stable, as both the lead ion and the larger complexes containing it are radicals. The same applies for lead, which can be found in such radical species. Numerous mixed lead oxides are known. When PbO2 is heated in air, it becomes Pb12019 at 293 degrees C, Pb12017 at 351 degrees C, Pb3O4 at 374 degrees C, and finally PbO at 605 degrees C. A further sesquioxide, Pb2O3, can be obtained at high pressure, along with several non-stoichiometric phases. Many of them show defective fluorite structures in which some oxygen atoms are replaced by vacancies. PbO can be considered as having such a structure, with every alternate layer of oxygen atoms absent. Negative oxidation states can occur as Zintal phases, as either free lead anions, as in Ba2Pb, with lead formally being lead, or in oxygen-sensitive ring-shaped or polyhedral cluster ions such as the trigonal bipyramidal Pb52 ion, where 2 lead atoms are lead and 3 are lead. In such anions, each atom is at a polyhedral vertex and contributes 2 electrons to each covalent bond along an edge from their sp3 hybrid orbitals, the other 2 being an external lone pair. They may be made in liquid ammonia via the reduction of lead by sodium. Lead can form multiply bonded chains, a property it shares with its lighter homologues in the carbon group. Its capacity to do so is much less because the Pb-Pb bond energy is over 3.5 times lower than that of the C-C bond. With itself, lead can build metal-metal bonds of an order up to 3. With carbon, lead forms organolead compounds similar to, but generally less stable than, typical organic compounds. This makes the organometallic chemistry of lead far less wide-ranging than that of tin. Lead predominantly forms organolead compounds, even when starting with inorganic lead reactants. Very few organolead compounds are known. The most well-characterized exceptions are Pb2 and Pb2. The lead analog of the simplest organic compound, methane, is plum vein. Plum vein may be obtained in a reaction between metallic lead and atomic hydrogen. 2 simple derivatives, tetramethyllead and tetraethyl lead, are the best known organolead compounds. These compounds are relatively stable. Tetraethyl lead only starts to decompose if heated or if exposed to sunlight or ultraviolet light. With sodium metal, lead readily forms an equimolar alloy that reacts with alkyl halides to form organometallic compounds such as tetraethyl lead. The oxidizing nature of many organolead compounds is usefully exploited. Lead tetraacetate is an important laboratory reagent for oxidation in organic synthesis. and tetraethyl lead was once produced in larger quantities than any other organometallic compound. Other organolead compounds are less chemically stable. For many organic compounds, a lead analog does not exist. Leads per particle abundance in the solar system is 0.121 ppb. This figure is 2.5 times higher than that of platinum, 8 times more than mercury, and 17 times more than gold. The amount of lead in the universe is slowly increasing as most heavier atoms gradually decay to lead. The abundance of lead in the solar system since its formation 4.5 billion years ago has increased by about 0.75%. The solar system abundances table shows that lead, despite its relatively high atomic number, is more prevalent than most other elements with atomic numbers greater than 40. Primordial lead, which comprises the isotopes Lead-204, Lead-206, Lead-207, and Lead-208, was mostly created as a result of repetitive neutron capture processes occurring in stars. The two main modes of capture are the S and R processes. In the S process, captures are separated by years or decades, allowing less stable nuclei to undergo beta decay. A stable thallium-203 nucleus can capture a neutron and become thallium-204. This undergoes beta decay to give stable Lead-204. On capturing another neutron, it becomes Lead-205, which has a half-life of around 15 million years. Further captures result in Lead-206, Lead-207, and Lead-208. On capturing another neutron, Lead-208 becomes Lead-209, which quickly decays into Bismuth-209. On capturing another neutron, Bismuth-209 becomes Bismuth-210, and this beta decays to Polonium-210, which alpha decays to Lead-206. The cycle hence ends at Lead-206, Lead-207, Lead-208, and Bismuth-209. In the R process, captures happen faster than nuclei can decay. This occurs in environments with a high neutron density, such as a supernova or the merger of two neutron stars. The neutron flux involved may be on the order of 1022 neutrons per square centimeter per second. The R process does not form as much lead as the S process. It tends to stop once neutron-rich nuclei reach 126 neutrons. At this point, the neutrons are arranged in complete shells in the atomic nucleus, and it becomes harder to energetically accommodate more of them. When the neutron flux subsides, these nuclei beta decay into stable isotopes of osmium, iridium, and platinum. Lead is classified as a chalcophile under the Goldschmidt classification, meaning it is generally found combined with sulfur. It rarely occurs in its native, metallic form. Many lead minerals are relatively light and, over the course of the Earth's history, have remained in the crust instead of sinking deeper into the Earth's interior. This accounts for lead's relatively high crustal abundance of 14 ppm. It is the 38th most abundant element in the crust. The main lead-bearing mineral is galena, which is mostly found with zinc ores. Most other lead minerals are related to galena in some way. Boulangerite, Pb5Sb4S11, is a mixed sulfide derived from galena. Anglesite, PbSO4, is a product of galena oxidation, and cerussite or white lead ore, PbCO3, is a decomposition product of galena. Arsenic, tin, antimony, silver, gold, copper, and bismuth are common impurities in lead minerals. World lead resources exceed 2 billion tons. Significant deposits are located in Australia, China, Ireland, Mexico, Peru, Portugal, Russia, and the United States. Global reserves resources that are economically feasible to extract totaled 88 million tons in 2016, of which Australia had 35 million, China 17 million, and Russia 6.4 million. Typical background concentrations of lead do not exceed 0.1 μg/m3 in the atmosphere, 100 mg/kg in soil, and 5 μg/L in fresh water and seawater. The modern English word lead is of Germanic origin. It comes from the Middle English lead and Old English lad. The Old English word is derived from the hypothetical reconstructed Proto-Germanic *luda. According to linguistic theory, this word bore descendants in multiple Germanic languages of exactly the same meaning. The origin of the Proto-Germanic *ʻlɛd is not agreed in the linguistic community. One hypothesis suggests it is derived from Proto-Indo-European *ʻlɛd. Another hypothesis suggests it is borrowed from Proto-Celtic *io. This word is related to the Latin plumbum, which gave the element its chemical symbol Pb. The word *io is thought to be the origin of Proto-Germanic *blua, from which stemmed the German blei. The name of the chemical element is not related to the verb of the same spelling, which is derived from Proto-Germanic *ladigen. Metallic lead beads dating back to 7600 BCE have been found in Asia Minor and may represent the first example of metal smelting. At that time lead had few applications due to its softness and dull appearance. The major reason for the spread of lead production was its association with silver, which may be obtained by burning galena. The ancient Egyptians were the first to use lead minerals in cosmetics, an application that spread to ancient Greece and beyond. The Egyptians may have used lead for sinkers in fishing nets, glazes, glasses, enamels, and for ornaments. Various civilizations of the Fertile Crescent used lead as a writing material, as currency, and as construction material. Lead was used in the ancient Chinese royal court as a stimulant, as currency, and as a contraceptive. The Indus Valley Civilization and the Mesoamericans used it for making amulets, and the Eastern and Southern African peoples used lead in wire drawing. Because silver was extensively used as a decorative material and an exchange medium, lead deposits came to be worked in Asia Minor since 3000 BCE. Later, lead deposits were developed in the Aegean and Laurion. These three regions collectively dominated production of mined lead until c. 1200 BCE. Since 2000 BCE, the Phoenicians worked deposits in the Iberian Peninsula. By 1600 BCE, lead mining existed in Cyprus, Greece, and Sardinia. Rome's territorial expansion in Europe and across the Mediterranean, and its development of mining, led to it becoming the greatest producer of lead during the Classical era, with an estimated annual output peaking at 80,000 tons. Like their predecessors, the Romans obtained lead mostly as a byproduct of silver smelting. Lead mining occurred in Central Europe, Britain, the Balkans, Greece, Anatolia, and Hispania, the latter accounting for 40% of world production. Lead tablets were commonly used as a material for letters. Lead coffins, cast in flat sand forms, with interchangeable motifs to suit the faith of the deceased, were used in ancient Judea. Lead was used for making water pipes in the Roman Empire. The Latin word for the metal, plumbum, is the origin of the English word plumbing. Its ease of working and resistance to corrosion ensured its widespread use in other applications including pharmaceuticals, roofing, currency, and warfare. Writers of the time, such as Cato the Elder, Columella, and Pliny the Elder, recommended lead vessels for the preparation of sweeteners and preservatives added to wine and food. The lead conferred an agreeable taste due to the formation of sugar of lead acetate, whereas copper or bronze vessels could impart a bitter flavor through verdigris formation. Heinz Eschnauer and Marcus Stoipler, Wine and Enological Specimen Bank, 1992. The Roman author Vitruvius reported the health dangers of lead, and modern writers have suggested that lead poisoning played a major role in the decline of the Roman Empire. Other researchers have criticized such claims, pointing out, for instance, that not all abdominal pain is caused by lead poisoning. According to archaeological research, Roman lead pipes increased lead levels in tap water, but such an effect was unlikely to have been truly harmful. When lead poisoning did occur, victims were called Saturnine, dark, and cynical, after the ghoulish father of the gods, Saturn. By association, lead was considered the father of all metals. Its status in Roman society was low as it was readily available and cheap. During the Classical era, tin was often not distinguished from lead. Romans called lead plumbum nigrum, and tin plumbum candidum. The association of lead and tin can be seen in other languages. The word olevo in Czech translates to lead, but its Russian cognate means tin. To add to the confusion, lead bore a close relation to antimony. Both elements commonly occur as sulfides, often together. Pliny incorrectly wrote that stibnite would give lead on heating, instead of antimony. In countries such as Turkey and India, the originally Persian name surma came to refer to either antimony sulfide or lead sulfide, and in some languages, such as Russian, gave its name to antimony. Lead mining in Western Europe declined after the fall of the Western Roman Empire, with Arabian Iberia being the only region having a significant output. The largest production of lead occurred in South and East Asia, especially China and India, where lead mining grew rapidly. In Europe, lead production began to increase in the 11th and 12th centuries, when it was again used for roofing and piping. Starting in the 13th century, lead was used to create stained glass. In the European and Arabian traditions of alchemy, lead was considered an impure base metal which, by the separation, purification, and balancing of its constituent essences, could be transformed to pure and incorruptible gold. During the period, lead was used increasingly for adulterating wine. The use of such wine was forbidden for use in Christian rites by a papal bull in 1498, but it continued to be imbibed and resulted in mass poisonings up to the late 18th century. Lead was a key material in parts of the printing press, which was invented around 1440. Lead dust was commonly inhaled by print workers, causing lead poisoning. Firearms were invented at around the same time, and lead, despite being more expensive than iron, became the chief material for making bullets. It was less damaging to iron gun barrels, had a higher density, and its lower melting point made the production of bullets easier as they could be made using a wood fire. Lead, in the form of Venetian ceruse, was extensively used in cosmetics by Western European aristocracy as whitened faces were regarded as a sign of modesty. This practice later expanded to white wigs and eyeliners, and only faded out with the French Revolution in the late 18th century. A similar fashion appeared in Japan in the 18th century with the emergence of the geishas, a practice that continued long into the 20th century. The white faces of women came to represent their feminine virtue as Japanese women, with lead commonly used in the whitener. In Africa, lead mining and smelting were known in the Benue Trough and the Lower Congo Basin, where lead was used for trade with Europeans, and as a currency by the 17th century, well before the scramble for Africa. In the New World, lead was produced soon after the arrival of European settlers. The earliest recorded lead production by European settlers dates to 1621 in the English colony of Virginia, 14 years after its foundation. In Australia, the first mine opened by colonists on the continent was a lead mine, in 1841. In the second half of the 18th century, Britain, and later continental Europe and the United States, experienced the Industrial Revolution. This was the first time during which lead production rates exceeded those of Rome. Britain was the leading producer, losing this status by the mid-19th century with the depletion of its mines and the development of lead mining in Germany, Spain, and the United States. By 1900, the United States was the leader in global lead production, and other non-European nations Canada, Mexico, and Australia had begun significant production. Production outside Europe exceeded that within. A great share of the demand for lead came from plumbing and painting. Lead paints were in regular use. At this time, more people were exposed to the metal and lead poisoning cases escalated. This led to research into the effects of lead intake. Lead was proven to be more dangerous in its fume form than as a solid metal. Lead poisoning and gout were linked. British physician Alfred Baring-Garrod noted a third of his gout patients were plumbers and painters. The effects of chronic ingestion of lead, including mental disorders, were also studied in the 19th century. The first laws aimed at decreasing lead poisoning in factories were enacted during the 1870s and 1880s in the United Kingdom. Further evidence of the threat that lead posed to humans was discovered in the late 19th and early 20th centuries. Mechanisms of harm were better understood, lead blindness was documented, and the element was phased out of public use in the United States and Europe. The United Kingdom introduced mandatory factory inspections in 1878.